Hello everyone, welcome to my channel. This channel is for educational purposes and we look at great theories of everything that I've gotten a lot of mileage out of, that I'd like to share, that you probably don't know about. We've done very deep dives on both the ancient Egyptian tree of life and the reciprocal system of theory from Dewey B. Larson. This is our 458th, I think, video that we've done on the reciprocal system. Mr. Dewey B. Larson was an engineer who lived in the United States in the 20th century. Around 1959, he proposed his two fundamental postulates, two simple sentences that described how the universe operated, that he gleaned from many years of inductive reasoning, poring over very great amounts of scientific data and trying to find, especially about chemistry, trying to find patterns, and eventually kind of stumbled across some relationships that gave him some epiphanies, and eventually put out his two fundamental postulates. Then he switched from induction to deduction and deduced a theoretical universe from the postulates. So a process of if this, then that, if this, then that, and he arrived at a theoretical universe, what the universe would look like if his postulates were correct. And then he compared his theoretical universe with the empirical universe of the modern scientists. In this book, he's doing that with chemistry. This book is called Basic Properties of Matter. And we're smack dab in the middle of chapter 7, called Temperature Relations. And so he's looking at really the temperature scale. But he comes up with equations for many of the basic properties of matter, like the melting point and the specific heat and the compressibility and the interatomic distance. And does it all from his two fundamental postulates. The first postulate is where primarily the reciprocal system is centered there, and that reads that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with two reciprocal aspects, space and time. And then the second postulate is more kind of take it or leave it, but really just saying that the process of science works, math works, logic works, geometry works. Sorry about that noise there. I think something's wrong with the heat in this place right now. Hopefully, it usually only lasts for a few seconds. But the second postulate is that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. And those are, I would have disputes with several prongs of that, but the general idea of the second postulate is that, okay, this is the math that we're going to be using in our process of deduction. These are the rules that we're going to be using to deduce from that first postulate to come up with our theoretical universe. We're going to be using the processes of math, we're going to be using geometry, and we're going to be using logic to figure this out. And whether you think it should be commutative mathematics, I think it should just kind of be simple mathematics. Whether it's Euclidean geometry or projective geometry or synergetic geometry, I don't think Larson was really splitting hairs about all that. I think he was just trying to say that we're using basically well-known forms of math and geometry in order to embark on our theoretical deduction from this first postulate. So the first postulate we'll pay attention to. The universe conforms to the universe is composed entirely of one component, motion. That's really the first aspect there. And motion exists in 3 dimensions. There's a second prong. Motion comes in only discrete units. That's the third part. And then motion has 2 reciprocal aspects, space and time. And that's where you get the name, the reciprocal system. Motion is the relationship between space and time. That makes space and time reciprocals of one another. And motion is basically a fraction with space or time as the numerator and time or the top of the fraction, and time or space as the denominator or the bottom of the fraction. You can see that clearly in speed. If you want to say the bike is moving 15 miles per hour, 15 miles of space in 1 hour of time, that is speed. And that is a relationship between space and time. Space over time is speed. And the reciprocal relationship can be singled out if you decide to double the speed. Now you can say the bicycle is now moving 30 miles per hour. Or equivalently, you can say the bicycle is now moving 15 miles per half hour. So you can either multiply the space by 2, or you can divide the time by 2. That shows also a reciprocal relationship between space and time. Larson basically extrapolates from speed to all scientific phenomena. He says that all of our scientific phenomena are forms of motion. Matter is a kind of motion. Energy is a kind of motion. Force is a kind of motion. Acceleration is a kind of motion. Electric charge is a kind of motion. Electrical capacitance is a kind of motion. Magnetic, permeability is a kind of motion. Surface tension is a kind of motion. Power is a kind of motion. Pressure is a kind of motion. They all have, space over time. I don't know what the word would be. Coordinates isn't quite the right word, but, they're all fractions with space or time as the numerator, time or space as the denominator, with time or space being able to have exponents. So matter, for example, is time to the 3rd power over space to the 3rd power. Density is time to the 3rd power over space to the 6th power. Pressure is time over space to the 4th power. Capacitance, well, there is some dispute about capacitance. We'll say momentum. Momentum is time to the 2nd power over space to the 2nd power. And so on. So every one of our scientific phenomena is a form of motion. And they all can be represented in space or time terms only. Now, when Larson is referring to motion, he's referring to a specific or really more generalized kind of motion that he calls scalar motion. A scalar motion is a motion that has a magnitude, but it has no specific direction. You can envision a scalar motion with a balloon, and you can put some dots on the balloon. You blow up the balloon, and all of the dots will be moving away from each other. Each dot will be moving away from each other dot. Each dot will be moving in every direction. So you can't assign a specific direction to it. They will all be moving in every direction. and that is a scalar motion. But that is really like a one-dimensional scalar motion. You have to keep in mind that there are 3 dimensions. That is part of that, the second prong of this first postulate, is that motion, space, and time come in 3 dimensions. Now, what's interesting about that, we can definitely get with the idea of 3 dimensions of space. Now, there are some geometers out there or abstract physicists or something that might tell you that there are more than 3 dimensions of space. But generally, we look at space as 3-dimensional, x, y, z coordinates, up, down, to the side, or forward and back. And Larson calls that coordinate space. 3 dimensions of space in a still frame. Space is still. But to go along with that spatial stillness, we have time as progressing. Time is always getting later and later and later, but in no specific direction, like on the surface of an expanding balloon. So we, in our neck of the woods here in the universe, we observe coordinate space and clock time. The clock is getting later and later and later. And space has 3 dimensions, x, y, z coordinates in a still frame background. Larson refers to this as the spatial reference system. Now, through extrapolation due to the reciprocal postulate, we can also, say that there is some place in the universe where there are 3 dimensions of time in a still frame. Coordinates, maybe not x, y, and z, but x-like, y-like, and z-like coordinates, perhaps I, j, and k, that are in a still frame, and we have progressing space or clock space. So this is coordinate time and clock space, the reciprocal of the spatial reference system that he calls the temporal reference system. Now, what's important, one thing that's important about this, you got 3 dimensions of space in the spatial reference system, 3 dimensions of time in the temporal reference system. But each one of those really only occupies 1 dimension of motion. Okay, if you have a 3-dimensional space, you really just need 1 dimension of motion to cover that. So there are extra dimensions of motion, 1 or 2, depending on whether the spatial or temporal reference system are inclusive, I guess. But there are dimensions of motion that go beyond the temporal and spatial reference frames, and that can't be described by those reference frames. That is, 3 dimensions of scalar motion. So we're looking at kind of a limited reference frames. Now, Larson also has what he calls the natural reference system. And this really has to do with the discrete unit postulate, which says that time, space, and motion all come only in discrete units. You have to have a full unit of space before you have space. You have to have a full unit of time before you have time. If you have 1 unit of space in 1 unit of time, Larson refers to that as unit speed. Space over time is speed. Unit speed is 1 over 1. 1 unit of space and 1 unit of time. Turns out that this doesn't turn out, it was really designed this way, but 1 unit of space and 1 unit of time is the speed of light. And this is the speed of the progression. So the progression, that outward motion of the surface of the expanding balloon, He calls that the progression. Now, if you take the balloon and you suck it in and deflate the balloon, all the dots will be moving toward each other. Larson refers to that as gravitation. And so this outward motion, the progression, occurs at the speed of light. 1 unit of space per 1 unit of time. Every step on that progression is 1 unit more of space and 1 unit more of time. So that outward motion is occurring at the speed of light. Larson refers to that as the progression of the natural reference system. This is the reference system that nature uses. Okay, the scientists use their spatial reference system, their stationary reference system. And Larson is really saying that that's why you're making so many errors. Now, what he also says is that science has made many miraculous, discoveries and miraculous applications of science, but that doesn't mean that they know what they're talking about. In general, he makes a distinction between mathematically correct and conceptually correct. He basically concedes that in most cases, the scientists have the math correctly. They have figured out the math correctly, but their interpretations of the math, their why of the math, like why is it like that, they come up with nothing in general, and they do not have a conceptually correct system. Larson steps in to correct the concepts behind the math. And he also provides the math. The math is generally identical to the math of the modern system, at least in terms of the macro, like Newtonian mechanics. And so we try to also then we figure out, okay, we've got this outward motion of the progression, the natural reference system. He also refers to this as the null point or the 0 point. I don't believe I've seen him refer to it as a 0 point. This condition of rest in the universe, or the empty universe. This is the universe that you have when you don't have anything. You have in a universe of motion, if you have nothing, you still have an outward motion at the speed of light in all directions, ensuing from every location at all times. Okay, it's omnipresent and eternal, and it is our source. So all of our matter, aggregates of matter, galaxies, and everything under that comes from that source of the progression, comes from taking that outward motion and somehow reversing it and harnessing that. And that process starts with the photon. The photon reverses the motion in 1 dimension, remembering that there are 3 dimensions. And then that photon gets rotated. So you start with the photon, which is really a vibrational motion, a sine wave, and then that photon is rotated again backwards in a direction, a scalar direction, opposite to the direction inward instead of outward, and rotating that in 3 dimensions will eventually give you an atom. You have to throw another photon in there. Which comes from combining 2 subatomic particles, which are it's just 1 rotation. If you have 1 rotation, then you'll end up with something like an electron. And then when you combine an electron with a neutrino, or something like that, with a what he calls a massless neutron or a muon neutrino, then you end up eventually you build up. So an atom is a combination of motions, and it's really Larson's periodic table of 3 numbers, A, B, and C. A and B are 2-dimensional rotations that alternate. You get one, and then you'll get the other, and then you'll get the other, and then you get the other. And the first one has to be used to nullify the progression. And then the other ones are going to be used to kind of categorize the periodic table for Larson. And then the third number, the C number, is an optional one-dimensional rotation in the opposite vectorial direction. And that number can be 0 in the noble gases, and it can be positive or negative, depending on whether you really have an electronegative or electropositive. And Larson uses those numbers to determine his basic properties of matter. Now, there are a few other things, but I'd like to go on and start reading from his book here, chapter 7, Temperature Relations. And I'll try to fill in the gaps, of which there probably will be very many. I would just suggest that you listen just to pick up some breadcrumbs in addition to what I've told you. And, you know, that's how you learn the reciprocal system. It's not going to be there on a silver platter for you. Larson did a phenomenal job, but he was just one person trying to put together an entire theory of everything, a universe of every subject. And he wrote on many, many, many subjects. Chemistry is just one of them. Okay, thermal factors of the elements for which reliable specific heat patterns are available. And again, specific heat is how much heat you have to add to a certain amount of matter to raise the temperature a certain, a certain amount. It's kind of the efficiency of heat. Thermal factors of the elements for which reliable specific heat patterns are available, and the corresponding theoretical first transition temperatures, T1, are listed in Table 22 together with the T1 values derived from the curves of the type illustrated in the figures in the previous chapter, in which the temperature scale is empirical. In effect, this is a comparison between theoretical and experimental values of the temperature scales of the specific heat curves. Okay, so Larson is putting his theoretical equations that are plugged into these the elements and the compounds and comparing them with the scientific tables. The experimental values are subject to some uncertainty, which is kind of a bugaboo for Larson. You know, he's trying to compare his theoretical values with the scientist values. In many cases, the scientist values are uncertain. So how's he supposed to compare them? As they have been obtained by inspection from graphs in which the linear portions of the curves were also drawn from visual inspection. Greater accuracy could be attained by using more sophisticated techniques, but the time and effort required for this refinement did not appear to be justified for the purposes of this initial investigation of the subject. And by the way, this was one of Larson's final books. He wrote this in 1987 and died in 1990. And if you are getting up in years, you can be inspired by the fact that Larson was about 89 years old when this book came out. And that really all of Larson's great works, some of his greatest works, came out when he was in his 80s or 90s. The compressibility factors derived in Chapter 4, with a few values restated in different but equivalent terms, are shown in the table for comparison with the corresponding thermal factors. The principal determinants of the compressibility values, aside from the effect of the pressure level itself, including the internal pressure, were found to be the magnitude and sign, positive or negative, of the displacement in the electric dimension. The rotational group to which the element belongs, determined by the magnetic displacements, is much less significant. In the thermal situation, the rotational group becomes the dominant influence. The elements of group 3b, magnetic displacements 3, 3, those are the A and B numbers. So these 3, 3 numbers, I think that is the line on the periodic table that starts with potassium. I might be wrong about that. But I think that's right. It might be rubidium. It might be the next number after that. So 37 to 54. Midway in the group order generally have thermal factors close to the compression values. In half of the 3b elements, these same ones, included in the table, the deviation is no more than 1 unit, but in each direction from this central group there is a systematic deviation from the compressibility values, upward in the lower group and downward in the higher groups. So Larson is just taking a look at the patterns that he has developed here, that these different atoms have different values for compression than they do for heat. And those heat and compression are really the two primary values that are occurring in what you call the time region, which I didn't really cover. But if we've got this progression of the natural reference system, that's really, Larson calls it the condition of rest. Now, in a universe of motion. That means that half the universe is moving faster than the speed of light, and half is moving slower than the speed of light. We really only know about the half that's moving slower than the speed of light. But he refers to these as that slower than speed of light is the material sector, and the faster than the speed of light is the cosmic sector. And basically, in the material sector, this is the sector we're familiar with. We have the spatial reference system, coordinate space and clock time. In the cosmic sector, faster than the speed of light, that's where we have coordinate time and clock space. And within each one of these sectors is a subregion that has to do with the discrete unit postulate. If atoms and particles of the material sector are approach each other and they get to 1 unit of space apart, which is approximately 2/millionths of an inch, they can't approach each other any closer than that because there is no such thing, because you have to have a full unit of space before you have space. So in order to continue on their course, they move outward in time instead of space. Time being the reciprocal of space, moving outward in time is tantamount or equivalent to moving inward in space. Did I say moving outward in time is tantamount to or equivalent to moving inward in equivalent space? Larson refers to it as equivalent space. But this is how atoms, so basically at this borderline, the unit speed boundary, he refers to this as the time region, moving into the time region where you don't have space anymore because you're less than 1 unit of space, so you only have time. But we perceive it in equivalent space because we are anchored to a spatial reference system. So we don't see time, we only see space, but we see equivalent space. And there are some caveats that we only can see a certain fraction of things when we're looking across into a boundary, into a foreign sector or region of the universe. But this is the realm of space and of matter, material, atoms and particles and compounds. And when you cross that boundary, the rules reverse. And now the progression, still outward in space, is inward in equivalent space. And gravitation is now outward in equivalent space. And that results in force equilibrium resulting, because the progression is constant, eternal, and omnipresent, and it's always the same. Gravitation increases or decreases depending on the distance apart according to the inverse square law. And so there's a point at which gravitation and the progression are the same, and that is the interatomic equilibrium. Now, once these atoms, groups of atoms or compounds, establish equilibrium among themselves, this is like a geometrical packing kind of situation in the solid state. Then they can also be affected by pressure and temperature. Pressure is really an internal pressure from the progression. The progression is moving inward in equivalent space. And so the progression creates an internal pressure, of which can also be added an external pressure when you're physically pressing them closer together. Temperature works the opposite way and tends to move them apart, and it is an appurtenance of gravitation, so or rotational factors of the atom, otherwise known as gravitation. And so Larson here is basically determining that there's a slight difference in the reactions that are involved in terms of compression as opposed to temperature. But in each direction from this central group, there is a systematic deviation from the compressibility values for temperature values, upward in the lower groups and downward in the higher groups. Every element above element number 42, molybdenum, that is included in the table, with one exception, has thermal factors either equal to or less than the corresponding compressibility factors. Every element below molybdenum, with 3 exceptions, 2 of which are alkali metals, has thermal factors that are either equal to or greater than the corresponding compressibility factors. So it appears as if the compressibility and the pressure and the temperature are moving in opposite directions. Okay, I believe that's all we're going to get to for today. I'm sorry that we're creeping through this very slowly, but there's obviously a lot of background information. You don't want to get bogged down in the details, but what's important is that you learn the concepts, because these concepts, this is a theory of everything. So the concepts can be applied to all subjects. This is just chemistry, but it applies to every subject. Okay, thanks for tuning in.